In the last few lectures, we were examining steady unidirectional transport under different conditions. The general equation for unidirectional transport in terms of the field variable in one coordinate, okay, one coordinate and time, okay, is the following. Okay. The time derivative of the field variable is equal to d by dz of the diffusivity times the gradient of the field variable plus the source. Field variable is concentration, temperature or velocity. The diffusivity is the mass diffusivity, thermal diffusivity, momentum diffusivity. The sources are mass source, momentum source and energy source. First we considered the simplest case where the diffusivity is a constant and there is no source, steady state. Okay, we are considering steady state in all cases. If there is no source and diffusivity is a constant, the flux is a linear function because the flux is obtained by, so the equivalent equation for the flux is going to be equal to partial of phi Fv by partial T is equal to minus partial Jz by partial Z plus source, okay, where Jz is just equal to either the mass flux, the heat flux or the momentum flux, which is the negative of the shear stress. Okay, momentum flux is the negative of the shear stress. Okay. Okay. So, that is the expression in terms of the flux. So, if there is no source, steady state, the derivative of the flux is 0, the flux is a linear function of position. If the diffusivity is a constant, no source, second derivative of the field variable is equal to 0, which means that the field variable is a linear function. Okay. If the source is a constant, sorry, if the source is 0, the gradient of the flux is 0, flux is a constant, field variable is a linear function. Source is a constant, flux is linear because it is one integral, field variable is quadratic, two integrals. Okay. So, we consider different examples of each of these, all for steady state where there is no time variation. Viscous heating in a channel, if the velocity profile is linear, the source is a constant, the source is a constant, therefore, the flux is a linear function of position. Okay. You recall that we had got this Qz, okay, here as a linear function of position. Qz was a linear function of position, that is, it was varying linearly with position. The field variable is one integral of the flux and therefore, it is quadratic if the diffusivity is a constant. Okay. And from that we got the relation between the Nusselt number and the Brinkmann number for this case. Same thing for the flow down an inclined plane. The force density is a constant, rho g sin theta, where theta is the angle of the plane from the horizontal. Source is a constant, the force density is a constant, the shear stress is a linear function because it is one integral. Okay, the shear stress is a linear function, rho g sin theta into h minus z. If the viscosity is a constant, if the diffusivity is a constant, then this velocity profile is quadratic because it is one integral of the shear stress, which is a linear function. So, you get a quadratic function, which is what we got for the velocity profile here, okay, which is what we got for the velocity profile here. And then we had calculated the maximum velocity, the average velocity, the ratio of those two was equal to maximum by average was 3 by 2, and then we also got a correlation for the Froude number, V average by root g h, which was Archimedes number to the half power in this particular case. So, that is a correlation for the velocity for the flow down an inclined plane between the dimensionless groups. Froude number, ratio of inertial and gravitational forces, Archimedes number, ratio of gravitational and viscous forces. A slightly more complicated example, flow of a power law fluid. Okay. Flow of a power law fluid where K is the flow consistency index and N is the power law index. Okay. So, therefore, the relation between the shear stress and the velocity gradient is nonlinear. Nevertheless, the balance equation in terms of the shear stress is exactly the same. The derivative of the stress plus the body force density equals 0. Okay. And therefore, this gives, if the source, the force density is a constant, this gives you a linear function for the shear stress, okay, which was the same as that what we had for a Newtonian fluid, okay, which follows Newton's law of viscosity. So, regardless of the constitutive relation, the relation between the flux and the source is the same. Okay. What changes is the relation between the flux and the gradients of the temperature, concentration or velocity. So, this constitutive relation is different, okay. This constitutive relation is different, and because of that the velocity profile is different. Okay. It goes as h power n plus 1 by n minus h minus z power n plus 1 by n, and this factor of n by n plus 1 when you do the integral. And from that we had got what was the maximum velocity and the average velocity, the ratio of those two. Okay. So, we got V max by V average is equal to n plus 1 by 2n plus 1. I am sorry, it is the other way around. Okay. And okay. That is because V average has n by 2n plus 1 here, whereas V max has n by n plus 1. Okay. So, V max by V average would be 2n plus 1 by n plus 1. And you can verify that this is the same result that you get for the Newtonian fluid for n is equal to 1, this ratio is 3 by 2 as we had calculated in that case. Okay. So, this is how we consider problems where either the source density is a constant, the flux, the relationship between the flux and the gradient could be linear or could not be linear. In either case, since the source is a constant, the force density or the mass production rate per unit volume or the energy production rate per unit volume, if that is a constant, the flux is a linear function, and then you use the relationship between the flux and the gradient in order to find out what is the profile. So, we will look at another example where the force density depends upon position, okay. And this is what are called electrokinetic flows. Okay. So, I will explain this flow in a little bit detail. Okay. So, if I have a fluid with ions, okay, a fluid with ions, okay, thickness h, and let us assume the surfaces were charged. Okay, let us assume that the surfaces were charged. Okay. Okay. And the fluid contains ions, so it will have positive and negative ions. Okay. And the fluid is on average neutral. Okay. Let us call the direction perpendicular to the surface as z and the direction along the surface as x. Okay. So, in this case, since the surfaces are charged, okay, let us call the surface charge density. QES, okay, ampere, sorry, it is charge per unit area. Okay. Charge has dimensions of ampere times second, okay, because current is charge per unit time, transport of charge per unit time. So, charge has dimensions of current into second divided by meter square. Okay, this is the electrostatic charge on the surface per unit area. This is called the surface charge density. Because the surface is charged, there is going to be a greater concentration of negative ions close to the surface, which are attracted by the positive charge of the surface. Okay. There will be a greater number of negative ions closer to the surface because of the positive charge of the surface. Okay. And this localization of ions, okay, okay, it is called an electrical double layer, that is restricted to a thin region close to the surface. Okay, it is restricted to a thin region close to the surface. Okay. So, if I plot the density, the charge density, okay, the charge density, okay, if I just look close to the surface, okay, and expand out the charge density, you will find that the charge per unit volume, the charge density is going to decrease exponentially from the surface. Okay. The charge density decreases exponentially from the surface, and that charge density is given by an exponential relation, okay, as a function of z. So, because the surface is positive, it is going to attract negative charges. So, therefore, there will be an excess of negative charges close to the surface. In the bulk, of course, the fluid is neutral. So, the number density of positive and negative charges is exactly the same. There is no net charge on the surface in the bulk, I am sorry. Okay. There is a net charge on the surface. So, that will attract charges of the opposite sign close to the surface. So, the charge density close to the surface will be of the negative ions will be higher, the charge density of positive ions will be lower. So, you will get a net charge density at the surface in this case, and this net charge density decreases exponentially due to the screening of the charges away from the surface. The charge density in electrostatic charge density in this case is given by QES by lambda d e power minus z by lambda d. Okay. So, that is the expression where lambda d is what is called the Debye length. So, this is the expression for the charge density close to the surface. As z increases, this decreases exponentially. Okay. The charge density at the surface itself is equal to the ratio of the surface charge density. Note that this surface charge density is charges per unit area divided by lambda d, which is a Debye length, gives you a charge per unit volume. Okay. Now, this Debye length, it depends upon the properties of the electrical properties of the fluid as well as the thermal properties. Okay. The expression for the Debye length, I will not bother to derive it. The expression for the Debye length close to a surface is square root of epsilon kBt by sigma Ni naught Ei square. Okay. So, let me explain the different terms in this. Okay. kBt is equal to Boltzmann constant into temperature, absolute temperature. Okay. So, this has dimensions of energy, okay. This has dimensions of joules. Okay. Okay. Epsilon is the electrical permittivity of the fluid. epsilon is the electrical permittivity of the fluid. This has dimensions which we actually calculated when we did dimensional analysis. Okay. This is usually written as the relative permittivity, okay, times the epsilon naught, okay, where epsilon r is the relative permittivity dimensionless, okay, and epsilon naught, this is also called the dielectric constant, okay, the relative permittivity of the fluid and the and vacuum permittivity, okay, and epsilon naught is the vacuum permittivity. This is a universal constant, the vacuum permittivity. This is equal to 8.85 into 10 power minus 12 kg inverse meter per minus 3 second power 4 angstrom square. Okay. So, that is the value of this vacuum permittivity. Okay. Number density of ions. This has dimensions of number per, okay, and EI is equal to charge on the ion. Okay. This has dimensions of ampere second. Okay. So, these are the terms in this equation, okay, for the Debye length. So, the Debye length basically gives you the length over which the charge density decreases to 0 near a charged surface. Okay. So, if you put a charged surface next to a fluid that contains ions, both positive and negative ions in equal numbers, because the surface is positively charged, for example, more negative ions will be attracted towards the surface, and those negative ions will have, okay, the density of those ions will be of this form, and I should strictly speaking put a negative sign here, because if Q on the surface is positive, the ions that are attracted are negative, okay, and this is the expression for the Debye length. Okay. Okay. And you can easily verify that this has dimensions of length. Okay. So, epsilon is kg inverse meter per minus 3 second power 4 angstrom square. This Boltzmann constant is an energy, kg meter square per second square. Force into distance, force is mass into acceleration. Okay. Okay. And you can verify that the angstrom, the dimension A will cancel out, because this has dimensions of A square, okay, in the denominator. In the numerator, and you have ampere second in the denominator. So, that will cancel out, okay, and the kg inverse in the numerator will cancel out with this kg here. Okay. In the numerator I have second power minus 2 and second power 4 in this, second power minus 2 here, okay, second power minus 2 in energy, second power 4, and I have a second square in the denominator. Okay. So, you can see that ultimately you will get dimensions of length. So, let us consider what is the value of this Debye constant for real situations. Okay. Okay. Calculate the Debye length for 1 millimolar aqueous NaCl solution at 300 K. The relative permittivity also called the dielectric constants of water is 80. Okay. So, we have to calculate what is the debye length when you put a charged surface in water which contains 1 millimolar aqueous NaCl solutions. So, first thing we have to find out what is the number density of the ions. Ni is equal to 1 millimolar. Okay. So, it is equal to 10 power minus 3. Okay. Kilomoles, moles per liter. 1 molar is 1 mole per liter. Mole per liter, liter is 10 power minus 3 meter cubed. Okay. And 1 mole is 10 power minus 3 kilomoles. Okay. So, is equal. So, let me just write this as okay, 10 power minus 3 into 1 mole is 10 power minus 3 kilomoles. Okay. And 1 liter is 10 power minus 3 meter cubed. Okay. 1 cc is 10 power minus 3 liter, 1 cubic centimeter, and 1 liter is 10 power minus 3 meter cubed. Okay. Per meter cube. Okay. 1 kilomole contains 6.023 into 10 power 26 ions. 1 mole contains 6.023 into 10 power 23 ions. Okay. So, this contains 6.023 into 10 power minus 26, 10 power 26. Okay. So, it's into okay, ions per meter cube. Okay. So, this is equal to 6.023 to 10 power 23. Of sodium plus. Okay. So, there are 6.023 into 10 power 23 ions per meter cubed of sodium, and there will be an equal number of chloride. Okay. Of Cl minus in a neutral solution. Okay. So, this is the number of ions. So, summation of NiEi square. Okay. So, Ei for charge on an electron. Okay. So, let me just do the charge in. Okay, is equal to 1.6 into 10 power minus 19 angstrom second coulombs. 1.6 into 10 power minus 19 coulombs. 1 coulomb is 1 angstrom into 1 second. Okay. Therefore, summation of NiEi square, number density is the same, charge has opposite sign. Okay. Ei for positive ion is positive, for negative is negative. However, Ei square is the same for both. It is exactly 1 charge for each sodium and 1 charge for each chloride ion. Okay. So, this is going to be equal to 2 times into 10 power 23 ions per meter cubed into angstrom second the whole square. So, this is going to be equal to 3.08 into 10 power minus 14 meter power minus 3 second power minus 2 a power minus 2 a square, I am sorry. So, that is the term in the denominator. Okay. Recall that the expression that I had, lambda d is equal to square root of epsilon k b d by sigma n I e I square. So, next I need to calculate what is epsilon. Okay. Relative permittivity is 80 for water and epsilon naught is 8.85 into 10 power minus 12 kg inverse meters per minus 3 second power 4 a square. Okay. So, this is equal to 7.08 into 10 power minus 10 okay, kg inverse meter per minus 3 second power 4 ampere square. Okay. And kBT is equal to 1.38 into 10 power minus 23 joules per Kelvin into 300 Kelvin. Okay. So, therefore, the Debye length lambda d is equal to square root of epsilon k b t okay. You can just do a quick dimensional check, angstroms will cancel out. Joules is kg meter square per second square. Okay. Therefore, the units of kg will cancel out here. Second power 4 per second square will cancel out. This meter per minus 3 will cancel out and I have a meter square. So, square root of that meter square will just be meters. Okay. And if you do this calculation, if you simplify this, you will get 9.75 into 10 power minus 9 meters, which is about 10 nanometers. Okay. So, that is the Debye layer thickness, okay, 10 nanometers for 1 millimolar solution. Okay. If I take a higher concentration of ions, say 1.1 molar solution, right, then the denominator will increase by a factor of this term will increase by a factor of 100, because if I take 0.1 molar, the denominator will increase by a factor of 100. Therefore, the value will decrease by a factor of 10. So, for 1 millimolar, okay, you get Debye length of 10 power minus 7, and for 0.1 molar, okay, this will be lower by a factor of 10. So, this will be equal to 9.75 to 10 power minus 10 meters. Okay. So, if I increase n by a factor of 100, lambda will decrease by a factor of 1 over square root of 100, which is 1 over 10. Okay. So that is the Debye length. Okay. Varies between 1 nanometer and 10 nanometers approximately for 0.1 to 1 millimolar solutions. Okay. So that is the Debye length. So we had started off discussing electrokinetic flows. Okay. So far I have only told you about the double layer. In the next lecture I will examine electrokinetic flows. Now that I have established the physical picture here of a thin layer between 1 to 10 nanometers at the wall where all the charges are concentrated. We will continue this in the next lecture. I will see you then.